Hi everyone, this is Worksheet 12.1, some example probability problems. The purpose of this worksheet is to help give you a little bit more practice on the rules of probability and applying them to actual problems, because I have to say, knowing probability comes in handy in a lot of life beyond just thermodynamics and physical chemistry. So I'm hoping that with this worksheet you'll get a chance to see some ways that you can apply the rules of probability. Okay, with that, let's go ahead and get started. The first problem asks, what is the probability of drawing a royal flush in poker? And if you've never played poker, then a royal flush is if you get an ace, a king, a queen, a jack, and a 10, all in the same hand. You draw 5 cards if you're playing 5-card draw poker, and if you get all 5 of those cards that are in the same suit, so they're all hearts or they're all diamonds or they're all spades or all clubs, then you get a royal flush, and it's like the best hand you could possibly get in all of poker. It beats everything else. So remember that in a deck of cards you have a total of 52 cards, and we start by recognizing that with the first draw there are 52 possibilities to begin with, and then we draw the second card and there are only going to be 51 possibilities from there, and then we draw a third card and there's only 50 because we've drawn out 2 so far. Then the next card, there's 49 possibilities, and then there's 48. Okay, and what this equals is 311,875,200 possible poker hands. All right. And so therefore, drawing an ace, a king, a queen, a jack, and a 10 of the same suit, say just for now it's all hearts, drawing 5 in that order is going to be 1 out of 311,875, 200 possibilities. So it's a very, very slim chance. But remember, we don't actually care what order we draw all these out. This is related to a permutation, but we actually want a combination. So the number of ways to draw out these 5 cards where we don't care the order that we draw them out, that's going to be described by a combination. And that equals 52 times 51 times 50 times 49 times 48 divided by 5 factorial. And another way to write this is 52 factorial over 5 factorial times 52, that's minus 5 factorial. And remember, this is combinations of hands where we actually don't care about the order of the cards drawn. And we can use that quantity to find the probability of drawing a royal flush of all the same suit, so all hearts. Probability of a royal flush of all hearts is equal to 2,598,960. But we can add up the probabilities of getting a suit of hearts or clubs or spades or diamonds. And so because all of those outcomes are mutually exclusive, so really the probability of getting a royal flush of any suit is going to be 4 divided by that same number. And the final answer we get is approximately equal to 1.5 times 10 to the negative 6. And that's the probability that for a given hand you'll have drawn a royal flush. Okay, the next problem involves taking an average of some numbers, and you've got plenty of practice, I'm sure, taking averages from elementary school and high school, but I just want to revisit the issue. Let's say that we have a set of numbers, and the numbers are 3, 3, 2, 2, 2, 1, 1. Okay? Now, if we want to get the average of this, then the average just equals all of these numbers added together divided by the size of the set. So 1, 2, 3, 4, 5, 6, 7. So it's going to be 3 plus 3 plus 2 plus 2 plus 2 plus 1 plus 1 divided by 7. And it turns out that if you were to plug this into your calculator, you'd find that the average number was 2. Okay? That's one way to get an average. That's the way that they taught you back in elementary school. But another way to compute the average is to count how many of the same number you have. Notice that I've got 2 3s, 3 2s, and 2 1s. So I could say that the probability of getting a 3 is 2 out of 7, and the probability of getting a 2 is 3 out of 7, and the probability of getting a 1 is, again, 2 out of 7. So if I want to get the average, then what I could say is it's going to be equal to 3 times the probability of getting a 3 plus 2 times the probability of getting a 2 plus 1 times the probability of getting a 1. And that's just 3 times 2 sevenths plus 2 times 3 sevenths plus 1 times 2 sevenths. And if you add all this up, you still get the same average. It still works. And I want to point out that the quantity of numbers of a certain number in a set is also known as the degeneracy. So the degeneracy of the number 2 is equal to 3, and the degeneracy of the number 3 is equal to 2, and the degeneracy of the number 1 is equal to 2 as well, because it's the count of the number of those items in the set. And the symbol we use for degeneracy is going to be G. So we would say that G of 2 equals 3, so on and so forth. That's the symbol they use in this book. All right, we're on to the next side of the sheet and on to the next problem. I want you to get some practice calculating the average and the variance of a continuous distribution. And in this case, we're going to be using something called a uniform distribution. So let's say that we've got x along this axis, and we've got the probability of x along this axis. And let's say that we've got some value 1 over a here, and then we've got a value a over there, and our distribution is just a block like this. All right. We want the average x, and hopefully it makes sense to you that the total probability of all possible outcomes is equal to 1, and that's because this probability is represented by a rectangle, so you multiply a times 1 over a, and that's going to equal 1, and so the probability of any outcome is 1. So that's good. And if you recall that finding the average of a continuous distribution is an integration over the domain of the variable x times the probability of a given x integrated over x, in our case, is going to be equal to an integral from 0 to a, because that's the domain of our distribution. And x gets left alone, but p of x just always equals 1 over a the whole time, and that dx stays the way it is. Now I can integrate this function. Remember, this is x to the 1th power, so that gets raised by 2. So I get x squared, and then I divide by what I raised it to, and then I've still got the 1 over a right here, and the boundaries are going to be from 0 to a. Okay, now let me plug those in. The average of x is equal to 1 over a times a squared over 2 minus 0 squared over 2. And this just equals a over 2. And that's the answer. It's the average of this distribution. And that makes sense, right? Because a over 2 is that spot right there. So you can see that it makes intuitive sense that that would be the average of the distribution. Okay, well, now that we've got the mean or average, let's go ahead and calculate the variance. And the variance is the average x squared. Okay, so in order to get the average x squared, we set up our integral again, but this time we're using x squared instead of x times the probability integrated over x. And we're just going to follow the same procedure here. This is going to be x squared times 1 over a dx. And when we perform that integral, we're going to have 1 over a times x cubed over 3 integrated from 0 to a. Those are the boundaries. And that becomes 1 over a cubed divided by 3 minus 0 cubed divided by 3. And in the end, we get a squared over 3. And that's the variance. And I can calculate the standard deviation of this distribution by taking the square root of the variance minus the average squared. Notice that there is a subtle difference between those two. And I could plug those in, and I get the square root of a squared over 3 minus a over 2 squared. And that gives me the square root of a squared over 12, I believe. And that's the standard deviation of this distribution. Okay, let's get to the last problem. We're going to find the average of an exponential distribution. And an exponential distribution looks different than the uniform distribution. Let's say I've got an x here, and the exponential distribution goes like this. And over here I've got my probability. And let's say that the problem gives you a distribution, but it's not normalized. What does that mean if it's not normalized? Hopefully from class you remember that means that the area underneath the curve that's given to you does not equal 1. But we're talking about probabilities here, so the area under the curve has to equal 1. So here's the non-normalized distribution. We're going to use g instead of p to represent the non-normalized one. E to the negative ax, like that. And what's a? Well, a is just a constant. It determines how flat or how steep that distribution is. Now, we're going to assume that the true probability distribution is going to be some constant. We'll just use the letter a to represent it, times the unnormalized distribution. So now we need to find a. We'll start by insisting that the area underneath has to equal 1. So 1 has to equal the integral from 0 to infinity of big A times e raised to the little a x dx, like that. We can pull the big A out of the integral, and if you remember how to take integrals of exponentials, then you will know that this results in 1 over a e to the negative ax, like this, evaluated at the boundaries 0 and infinity. I'm missing a negative sign there, sorry. So 1 equals negative big A over little a, and then e to the negative a times infinity is going to be inside there, minus e to the negative a times 0. Now this just goes to 0, because e way off in the infinite direction just approaches closer and closer to 0. And this spot right here is just 1, because e raised to the 0 is just 1. So we've got a negative 1 left over inside these brackets, and we're left with this equaling positive big A over little a. And now if I just move if I multiply both sides of this equation times a, then it's clear that big A equals little a. Which means that our probability distribution equals a little a times e to the little a x, like that. Cool, now we can get our average x, and we'll do that in exactly the same way as we did with the uniform distribution, an integral from 0 to infinity of x times the probability of x dx. And when I write out those values, x times a e to the negative ax dx, like this. And you could use integration by parts to solve this, or you can just look it up in an integral table. And I'll just tell you what the answer is right now. This becomes negative e to the negative ax, x plus 1 over a. And this is evaluated on the boundaries 0 to infinity. And if you plug everything in, you get 1 over a, interestingly. So the average value, if that's a right there, because you can plug in 0 into the probability distribution here, and then the e to the negative ax becomes 1, so the probability is a right there. And I would say that the average x 1 over a is right around in there somewhere. So that's the average of that distribution.